Tonight's presentation is titled Feeling Small in a Big Cosmos by Dr. Shane Larson from Northwestern University. The universe is vast beyond anything humans can easily comprehend, and it is easy to become overwhelmed by the immensity, disheartened by how insignificant we seem. But in the vastness, there is a glimmer of truth that we should hold on to and use to guide us. In all the vastness we are, so far as we currently know, the only beings capable of asking questions about our existence and our place within the cosmos. We are the stars, come to life for the sole purpose of asking where we came from and why are we here. Such questions are deep and philosophical, but Shane likes to think we are here because the universe made us in an attempt to figure out why it is here. We are the universe looking at itself. We are the cosmos made manifest. Shane Larson is research professor of physics at Northwestern University, where he is associate director of Sierra. He works in the field of gravitational wave astrophysics, specializing in studies of compact stars, binaries, and the galaxy with both the ground-based LIGO project and future space-based observatory LISA. He grew up in Eastern Oregon and was formerly a tenured associate professor of physics at Utah State University. He's an award-winning teacher and a fellow of the American Physical Society. He contributes regularly to a public science blog at writescience.wordpress.com and tweets with the handle Science Jedi. Please welcome back Dr. Shane Larson. As a courtesy to our speaker and fellow members, please remember to silence your personal devices.
Thank you. Can everyone hear me without the mic?
Yeah.
If I use my professor voice? Okay, I'll do that. Because I tend to wave it around, and sometimes I let go of it, and it's a problem. So anyways, it's good to be back. It's good to see all of you. I keep track of all the talks I've done, and I've lost count of how many times I've come to talk to y'all. So it's good to be back. We did a couple during the pandemic. And so it's kind of good to be in person and see all of you again. So when Kurt contacted me, he asked for a long list of talks that I could do. So this is one of many, and it's one of my favorites. I actually wrote this talk because of a friend of mine, Jane Beachy, who works at the Illinois Humanities Council. And she mentors artists the kind of way I mentor young physicists, and she wanted an opportunity for them to expand their horizons and think about science and kind of connect to the universe in different ways than ordinary people do every day. And so we wrote this talk originally to kind of help them, understand what we do as scientists. And it's been very popular. It's a talk that I really like giving. It has that kind of, to me, kind of deep, kind of broad, poetic Carl Sagan feel to the way we all think about the universe when we stand out at night with the telescope. So I hope you enjoy it. We'll kind of take questions at the end, as always. As we go along, let me know what you think, okay? As always, you're going to think about this afterwards. You'll have some question a couple of weeks from now, okay? And my email address is right there. Don't forget the dot after the S. It looks like a star in the slide. And if you have questions, you can certainly email me, and I'll do my best to give you something to read, a YouTube video to watch, try and answer your question, whatever, okay? I'll have reading for you at the end, as I always do, and we'll see where we end up, okay? Okay. So, this is a site that most of us who are engaged in amateur astronomy are familiar with. If you get away from the city lights out to where it's dark, you go where I grew up in the Rockies, where you have Bortle 1 skies right outside your back door. You walk out and you can't see anything except the Milky Way and the stars overhead. I lived in Montana for many, many years. This is outside the Grand Tetons there, and there's a reason we call it Big Sky Country. That sky above you is just enormous, and even if you're not an astronomer, it's not difficult to stand there and be overwhelmed by how big the universe seems compared to what you experience in your everyday life. Even when you're out in the middle of nowhere looking at the vast expanses of the Earth, you definitely get the sense that the universe is far larger when you look at the sky. Carl Sagan, in the opening sequences of Cosmos, said it quite well. He said, the size and age of the cosmos are beyond ordinary human understanding. lost somewhere between immensity and eternity, is our tiny planetary home, the Earth. And this is, I think more than anything else, Sagan was very good at the poetic side of science and captured in many ways what I feel like we feel like standing out with our telescope when we're in the evening looking at the night sky. So let's start with this, and we'll use this as the launching point to talk about how big the universe really is and how we've come to understand and how we talk about those scales that we're faced with. So it all begins here. Okay, so this is the blue marble. How many of you have been following the Artemis? Yeah, okay, so Artemis for the first time went to the farthest orbit around the moon. It turned back and took a picture of the Earth and the moon together. Okay, actually I shouldn't say the only other. The first time that was ever done was in 1979 by the Voyager spacecraft. So Voyager 1 was the first time we had ever taken a picture of the Earth and Moon together, and now Artemis is out doing it on regular flights, or what we hope to be regular flights around the moon. But what's important about this image is that I can put this image up in any room, whether it's amateur astronomers or not, and every single person in the room will recognize it. They will know that this is the Earth. But if you think about it, there are only 24 people who have ever seen the Earth like this, and a significant fraction of them have died. Okay? And those are the Apollo astronauts. The astronauts who fly on the space station, the space shuttle, go into orbit around the Earth, they never see the entire Earth by itself. Only the Apollo astronauts and our spacecraft have ever done that. And the fact that that's true, but I can put this image up and everyone in the room recognizes it, is really a testament to our ability as humans to capture something that is impossible for us as ordinary individuals living our lives ever to see, and spread it around the world so effectively that you cannot find a person who doesn't recognize it. That is an amazing feat of sharing knowledge and understanding about our home and the place in the universe that we live. There's virtually no other piece of knowledge that you can imagine, that you can name, that has been spread as effectively as this image. Okay? So keep that in the back of your mind, and we'll use that as our foundation. Okay? Now, as astronomers, we often say, and I will say it during this talk again, the Earth is the very first thing we discovered in astronomy. But it's not what we think about when we think about astronomical discovery. What we normally think about are great devices. Okay? What's this? This is the Hubble Space Telescope. Okay? It is arguably the most successful scientific instrument ever built in human history. Okay? It's past its 30th birthday now. It is still going. We were getting ready to plummet it into the Pacific Ocean when it died, but now we're like, oh, it'll be so sad. Maybe we should see if we can fix it, right? And so we'll see how long it actually lives, okay? But our attachment to this, and in particular for those of us in this room right now, is because all of us have grown up during the space age, during the late space age, and we have learned to understand and perceive and think about the universe through images taken with this telescope. There have been some 20,000 papers written, scientific papers written, about the images taken with the Hubble Space Telescope. Okay? It has seen farther and discovered more than any scientific instrument in history. So, let's just talk about one thing that it did. Okay? So, if we go out, if my clicker works, if we go out tonight, Orion will be rising up, if you can get away from the city lights, and stretching out from the knee of Orion is Eridanus, the Great Sky River. Okay? And there are several places in the sky where we did this, but in particular, in this bow of Eridanus, between Eridanus and Fornax, there is an empty spot in the sky, where if you and I go out and we look, we don't see squat. There is nothing there. It's an empty spot in the sky. So, being professional astronomers, we're like, perfect! let's ask Hubble to stare at that spot in the sky over and over and over again for 10 years until it had stared at that spot for more than 20 days of photographic exposure time. And let's stack all those photos together and let's make an image of what Hubble can see in an empty spot in the sky. Okay? That image and others like it are called the Hubble deep fields. And if you were to hold a dime up at arm's length, the size of the picture I'm about to show you is the size of Roosevelt's eye on that dime held out at arm's length. I should have told you all to bring a dime tonight. Okay? Okay, yeah, it's pretty small, right? Okay, so the picture that resulted is called the deep field, and this is it. Okay? It is arguably the most remarkable image of the universe that humans have ever taken, because it's a picture of an empty spot in the sky, but it's full of stuff. And every fleck of light, every speck of color, every smudge that you see in that picture is a distant galaxy somewhere else in the universe. A shoal of stars and gas and dust full of other places, not unlike the places you and I know about here close to home. Now, this is called the Hubble Extreme Deep Field. And the question is, why do we take pictures like this? Well, our goal was we wanted to know how many galaxies are there in the universe. So you take a picture like this, you count all the galaxies in the picture, you multiply by the number of Roosevelt's eyes that cover the entire sky, and you get there are some 500 billion galaxies in the visible universe. Now, we're astronomers. We say stuff like that all the time. 500 billion galaxies. Like we know what 500 billion galaxies is. Okay? How long, if you counted 1, 2, 3, one number a second, how long would it take you to count to 1 billion? 31 years. Okay? More than 31 years. So to count to 500 billion, right? You can do multiplication. Okay? So this is the beginning of big numbers. This is what we mean when we say the universe is beyond ordinary comprehension. We can write down that number, but we have no practical experience to tell us what 500 billion galaxies really means. But we talk about it blithely. I'm guilty of it as a professional astronomer. You're guilty of it as amateur astronomers. People walk up to your telescope and say, how many galaxies are there in the universe? You're like, oh, about 100 billion. Okay, sure. Okay? It doesn't capture what it really means to be that big. So we need a different word. Okay? So this is what we say. We say the universe is ginormous! Because it's the only word I can really give you that really captures that it's really big beyond comprehension. Okay? Now, that was the Hubble Extreme Deep Field. That is not the end of the story. How come? Because there's a new kid on the block. Okay? So this is the James Webb Space Telescope. Okay? And just to show off, they said, let's have it do a deep field. We're only going to give it 12 and a half hours. And we're going to release that picture as its first picture. Okay? So the first light image from James Webb is this one. Okay? There's also a companion Hubble image. This is one of Hubble's other deep fields. Okay? You can see a couple of stars here. Okay? So this isn't quite as empty of a spot. Okay, but you can count the number of stars. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 stars. And every other fleck of light that you see is another galaxy. This picture is particularly notable because you'll see these very long, smeared out bananas, and those are also galaxies. But they're funhouse images of galaxies, distorted by the gravity of all of these galaxies in the middle of the picture. Okay, that's something called gravitational lensing. It's all about dark matter and stuff like that, and we'll talk about that in some other talk. Okay, but this is James Webb showing off, and this is what the next 20 years is going to be like for all the 6- and 7-year-olds you know who are going to grow up learning about the universe through the eyes of the James Webb Space Telescope. The same way you and I grew up learning through the eyes of Hubble. So that number, that 500 billion, I full well expect to go up.
Is that picture less than 1 arc second on a side?
I should know that, but my guess is yes, close to it, but I don't know the exact diameter. Okay, you can look it up. It's on the image page, but I don't have it off the top of my head.
Shane, before they did all the multiplication, how many galaxies were in the extreme deep field?
Okay, so so the question is, how many galaxies were in the deep field before you do the multiplication? So that number keeps changing because they're getting better at calibrating the image, even Hubble's image, right? So when it first started out, there were about 5,000, okay? And then that number went up by something like a factor of 2 or 3 before they were all done. So roughly 5,000 in that extreme deep field I showed you. Okay? Other questions before we go on? Okay. Okay, now, this is a big number, 500 billion. But there are other big numbers in the universe. Okay, so when my daughter was young, we used to go to the beach. Okay, and you know, this is in Utah, but you can go to the beach here in Chicago. And she looks at the beach and she asks, how many grains of sand are there on all the beaches of Earth? Brilliant question, right? And of course, we can answer that question. How do we do it? We do it exactly the same way we count galaxies. I go down to the beach, I pick up a handful of sand, I count how many grains can fall out of my hand, and then I multiply up to get all the beaches and all the deserts of Earth. Okay? And if I do that, I will get that there are about 10 billion grains of sand on planet Earth. That's count to 1 billion, 31 years, 10 billion times. How old's the Earth? 4.5 billion years old. It takes you 31 years to count to 1 billion. You have to do that 10 billion times. It will take you 300 billion years to count all the grains of sand on planet Earth. But we can figure it out because we can count a few and we know how to do math. We can answer unanswerable questions by being methodical about how we gather information and how we use that information to describe the world around us. Okay? But this number is tiny. Even though it's big, it's tiny. Because you could go back to the galaxies, and even though there are about 10 billion grains of sand on Earth, you could ask, how many stars are there in the universe? So I count how many stars there are in the Milky Way. I assume all those galaxies are kind of like the Milky Way. That's not perfect, but it's pretty good. And I multiply the two numbers together. And I get that there are 100,000 billion stars in the entire universe. And we say this like we know what it means. It's the right number. It'll go up and down by a factor of 10, 100 in my and your lifetime as we find more galaxies in more deep fields. But this is approximately the right number. A 1 followed by 23 zeros. And this isn't even a big number as far as the universe is concerned. Okay? 100,000 billion stars in the cosmos. And I can figure it out because I know how to count and I know how to use that knowledge to tell me about things that I can't practically count. Okay? So the question becomes, when everything is so impossibly far away, no one's gone out and counted all the stars in the Milky Way. No one's been farther than the moon, as we discussed a moment ago. Okay? When everything's so far away, and when the cosmos is so full of so many things, how do we figure out anything? Okay? And there's a very simple answer to that question. We ask questions. Okay? Carl Sagan once likened this to playing 20 questions. Remember those kids we were talking about? This is their favorite game in the world. Okay? How many of you have played 20 questions? Oh, good. How many of you have never played 20 questions? Oh, perfect! Okay. Oh, okay. Well, now's your chance, because there is something under that question mark. Okay? Okay, let's do it. Let's do 3 questions. It'll take us forever to do 20. What are your 3 questions? No, they have to be yes-no questions. Sorry. The rules of 20 questions are you must ask yes-no questions. Three yes-no questions. Is it an animal? No.
Vegetable.
Is it a vegetable? No.
Is it a mineral?
Is it a mineral? No. Okay, now we've just asked 3 questions. Okay? But with just 3 questions, you have eliminated vast quantities of everything in the universe. It's not any life form you've ever heard of on planet Earth. It's not any life form on any other planet, even though you haven't heard of it, provided those life forms could be classified as plants or animals. It's also not any mineral. So it's no chemical combination of things that look like rocks, which the universe is full of. If we went through 20 questions, you would be able to very rapidly converge on what is underneath that question mark, and eventually realize it's 3 astronomers. You might even realize they were Lego astronomers. I guarantee your kids would have gotten there. Okay? But that's amazing. The universe is full of stuff that we don't know anything about. The volume of science books in the library is enormous. But every one of you, despite the fact that most of you are not PhD scientists, I think, okay, just asking simple questions allows you to parse everything that the universe is into something that is understandable. And that's all we do as professionals. We call this game science, and we do it with everything in the universe. Every single day we get up and go to work. And all of you do it too. And that's the amazing thing about how we figured the universe out. When astronomy started, there were not professional people like me. There were amateurs like all of you. And in fact, amateur astronomy was the science of astronomy for many centuries, until almost the 20th century, before it became a profession. And everything that we knew of up to the beginning of professional astronomy, and still stuff that we know of today, is being discovered by amateur astronomers and professional astronomers. All because this is all there is to it. We discover the cosmos by asking questions about it. Okay? So I want to do an exercise with you. Does anyone recognize this? Okay, this is the bane of our existence. Light pollution writ large. Okay? But from orbit, you can see the cities of North America. This is where you and I are. We're probably out here somewhere, right? Okay, there's that must be Milwaukee. This must be Indianapolis. What is that? St. Louis. Okay, and on down the line. Okay? It's very hard to remember what it was like before we were able to take pictures like this. Okay? We live in an age, as we were saying a moment ago, where information is at our fingertips. Now, some of us can remember where we had to actually go find an encyclopedia. But these days, we all have magic devices in our pockets where we can figure out any piece of information we want right away. Okay? But I think it's important to kind of step back from that reality of our world and try and remember what it was like before. Okay? So it's hard to do that, even for those of us who have lived in the time before we had cell phones in our pockets, right? It's very hard to do that, but it's very instructive, okay? Because what I want you to do is I want you to go back to that time before we knew all those things about the universe that you know, to try and rediscover anew how remarkable it is, to understand how vast and how incomprehensible sometimes the cosmos really is. Okay? So, try and forget what you've been taught, and let's take a little journey. Now, this is what you and I do, right? We stand outside and we look at the sky. Okay, so what's this? Moon. Okay, these are planets, and you may be able to guess which ones they are, but Mercury, that's Venus, and that one's Saturn, actually. So this is from 2005, I think. So, okay? So this is what the sky looked like before we had telescopes. For 40,000 generations of human beings, everything that we knew and understood about the universe was discovered with the naked eye, which some of us still do. Okay? We always encourage people to go out and look with their naked eye, right? All the time. Because it's a way to connect with the cosmos. Okay? So, there was not too long ago, when you went out in the night sky, you could point to these things and say that's Mercury, Venus, and Saturn, but that's all you knew was what their names were. We didn't know anything. And even more remarkably, we didn't know anything about that object right there either. Okay? So, my clicker works sometimes, but not other times. Tell me some things you know about the moon.
Made of green cheese.
Everyone always knows that. Okay. What are some things you know about the moon?
240,000 miles away.
It's 240,000 miles away. Some of us have cars that have driven that far.
It's a quarter the size of the Earth.
It's roughly a quarter the size of the Earth.
Volcanically dead.
It's volcanically dead.
Tidally locked.
It's tidally locked, which means the same side of the moon faces the Earth all the time.
It takes about a month to go around the Earth.
Takes about a month, 29 days to go around the Earth. What about the moon itself? What do you know about
Basalt.
it? What?
Mostly basalt.
It's mostly basalts.
Created by a collision.
Ah, yeah, created by collision. That's a good one. That's only been in my professional lifetime we figured that out.
No atmosphere.
No atmosphere. Okay. All of these things we have learned because we have telescopes, because we've sent space probes there, because we've sent astronauts there. But for 40,000 generations of human beings, the only view you had was the view that I just showed you. Okay? So, if you go to Adler, you will see this. Okay? So this is a model of the moon made in the 1950s, I think, by the Rand McNally Corporation. Okay? You can stand about 5 feet away from it. It'll look just like that picture. Okay? Only half of it is there. How come? Because no one had ever seen the other frickin' side. Okay? But, let me ask you. We know the moon has mountains and craters because we've been there. And when you stand 5 feet away from this model, you can see the moon has mountains and craters. Okay? But, how far away from this globe would you have to stand for this to look exactly like the moon in the sky does in terms of its size? It's about 5 feet across, so it's about my height. How far away would you have to stand from this for this to look like the moon in the sky?
100 feet?
Say 100.
100 feet? Anyone else? 100 feet?
Half a mile.
Half a mile? Okay, so we got extremes going on there. Okay. About 140 meters. So football field plus the end zones, roughly. So we go and break into Adler tonight, we'll grab it off the wall, we'll haul it over to Soldier Field and put it on one end, and then we'll all run down to the other end and take a picture to prove to ourselves that what I just told you is true, and then we'll put it back. Don't tell the Adler I said that. Okay. Okay, so this is what it looks like if you do that. If you stand 140 feet away from that globe, it will look just like the moon does in the sky. And in this view, how big is it?
Half a degree.
Half a degree. Have any of you done the AL lunar observing? They make you do this. Okay, yeah, it's about the size of our dime. Okay, so if you hold a dime up, it's the same size as the moon. Okay, but you cannot see any mountains or craters or basalts or atmosphere or anything that you and I know about the moon. All you can tell is it has light and dark spots. Some people with very acute vision can tell that Aristarchus is there, but it's just a bright spot. So what changed our view of the moon? Telescope. And it was the very first thing Galileo looked at. There's probably an apocryphal tale that when he first used the telescope, he couldn't believe what his eyes were showing him. And so he took an Italian lira, a coin, and set it up on the far side of his courtyard, and went over here with his telescope and looked at that coin through the telescope and sketched it, and then went and looked at the coin this close to prove to himself that the telescope wasn't lying to him. Because when he looked at the moon through his telescope, this is what he saw. The moon that you and I know. The universe got immeasurably more complicated because we invented technology to make our eyes bionic. And this is what he wrote. The moon certainly does not possess a smooth and polished surface, the prevailing belief, okay? But one rough and uneven, and just like the face of the earth itself, everywhere full of vast protuberances, deep chasms, and sinuosities. And what's remarkable about that is not what he saw, but what you see him doing, comparing it to the earth. This is something that we do all the time in science. This is the Copernican hypothesis made manifest, that there's nothing special about Earth, that everywhere in the universe is kind of the same, and if I see something that looks like mountains on the moon, then it's going to be just like the mountains on the Earth. Galileo was a proponent of the Copernican hypothesis, and you can see it pervading his descriptions of what he thinks the universe is doing, right here.
And that's what caused all the trouble.
And this is part of what caused all the trouble.
Here, the
Exactly.
moon to the earth.
That's right. Okay? So, of course, it didn't end here. Once he figured out some things look different, he looked at everything. Okay? So, if we go back to our other things we could see in the sky, okay? Here's another planetary conjunction. So this is Jupiter and Venus. And to your naked eye, how big are Jupiter and Venus in the sky? Not very big. They're about the size of Roosevelt's eye when you hold it up there. Dime is the most important astronomical instrument. Okay? Okay, but when Galileo looked at the planets, he discovered that they were planets. What you and I think when we say the word planet, that they are worlds. And what we often forget is, yes, he discovered the planets were worlds, but what that meant he really discovered is that the Earth is a world. It's not the world, it is a world. Okay? And his sketches of the planets are famous. Here's his early pictures of Saturn, which he didn't realize had a ring. He thought it had ears. He realized Venus goes through phases, which tells us it's closer to the sun than we are. Okay? And Mars and Jupiter for him were featureless. Okay? His telescope wasn't that great. Okay? It's one of those Christmas telescopes he got. Okay? So, the planets are not stars, but the Earth is one of the planets. That's the thing that he really discovered. So let's talk about the planets a little bit, because they also have some interesting stories. Tell me what you know about Jupiter.
Very big.
Very big! The king of the planets. Okay, what else do you know about Jupiter?
That's a great red spot.
The Great Red Spot, okay? A hurricane-like storm that's the size of 2 or 3 Earths. It's been there for 400 years. What else?
More road gas.
Magnetic field.
Lots of gas, magnetic fields. What else?
A lot of moons.
Rotates very rapidly. What did it get said over here? I missed that.
A lot of
Spots.
moons.
Lots of moons. Okay. So Jupiter, through the telescope, through our telescopes, is infinitely better than Galileo's original telescope were. And you can see many of those things that you all just said. In particular, the Great Red Spot. How many of you have seen the Great Red Spot? Okay. Or as my astronomy mentor told me when I was learning amateur astronomy, the sorta okay red spot. Right? Okay. It's not easy to see all the time, but it's there. You can see the bands on the planet, even from here in Chicago. But in particular, you can see the Galilean satellites going around it. Okay? And this was the discovery that the moon is not unique. That the moon, is a satellite. And other worlds have satellites too. Okay? So in just this very short span of time, Galileo took a very simple scientific instrument and expanded our understanding of the universe by tremendous amounts. Arguably by amounts that are still causing confusion and reeling today. Because we got used to this idea that we have to be able to suddenly let go of everything we once believed and start afresh. And it still happens today, every single day in astronomy, just like it happened back then. Okay? Now, of course, once you can see stuff like this, you want to see it better. We have a name for that in amateur astronomy. We call it Aperture Fever, right? You gotta build a better instrument. But NASA's like, screw telescopes. If we want to see this place up close, a telescope ain't going to cut it. So let's build robots. Okay? What's this robot?
Voyager.
This is Voyager. Okay? Voyager 1 and Voyager 2 are still going today. Every year, they ask NASA, when are they going to die? They say in about 10 years. They've been saying that for 20 years. Okay? And they're still going. They're now at 150 astronomical units. Okay? So they're 3 times farther out into the universe than, I was going to say the planet Pluto. I will say the planet Pluto. We can argue about that if you want to. They are beyond the boundaries, we think, of where the sun exerts its influence on the space around it. In the same way that Hubble has done more than any telescope in history, these 2 spacecraft have traveled farther and discovered more about our local neighborhood than any spacecraft in history. And they're still going on. We sent them to Jupiter to do lots of things. Measure magnetic fields, count particles, do all those things. But the most precious cargo for us as humans that any spaceship sends back to Earth are pictures. And so there are thousands of Voyager pictures I could show you, but I'm going to show you my favorite. Okay? And this one is my favorite. Okay? And this one is my favorite because if I hung it up, if I printed this out on a 5-foot canvas and hung it up in my house and didn't invite any of you over, okay, anyone who walked in my house would be like, wow, that's such amazing modern art. Who's the impressionist? Right? And you're like, nature. Right? Nature uses planets as canvases. Okay? And this is why pictures are so powerful. And you and I know this as amateur astronomers. We can show someone a picture of the cosmos, whether it's a Hubble deep field, a picture of the Andromeda galaxy, a picture of Jupiter returned to our planet by Voyager. And someone who's not a scientist will feel the depth of emotion that the universe has to inspire in all of us. That very same picture I can take as a scientist and compute the fluid dynamics of the clouds of Jupiter. or take the multicolor pictures and tell you what the composition of the clouds are, or measure how high they are or how fast they're moving. The reason we take pictures is multifold. And it's not just for us as scientists, it's not just for us as astronomers, it's for everyone. Because it serves as a canvas to help us all understand what it is about the universe that's so special, and why it's important that we're capable of understanding it. Now, this is my favorite picture of Jupiter, but it's not the most famous picture that Voyager ever took. The most famous picture Voyager ever took is this one. Okay? Does anyone know which one this is?
Pale blue dot.
This is the pale blue dot. Okay? So that is Earth right there. In 1997, I think it was, Voyager was well past the orbit of Neptune. They asked Voyager to turn around and take a series of 72 mosaics pictures together to make a family portrait of all the planets around the sun. And you can go get the frames, you can see all of the planets. But this one is the one that captures the attention. There's a lens flare off of the camera. Those of you who are photographers will be familiar with this. So this is a lens flare from the sun, and it just so happened that the Earth was caught in that lens flare. Okay? And Carl Sagan famously noted this and called this the pale blue dot. There's a famous soliloquy. There's actually a recording of him reading it. When he wrote his books, he would often dictate them, so I think that's where it came from. But it's probably one of the most recognized and important passages in scientific writing ever written. So if you've not seen it, you can go to YouTube and listen to Carl say it. There's a recording of me doing it on YouTube. There's all kinds of people who've done this, but you can also read it. There's a book by this name that's quite fantastic. But it's about what you and I are talking about tonight. It's about the fact that in all the vastness of the universe, that's home. It's very small, it's very insignificant, and even from up close, it's hard to notice that it's there. And that inspires, in some people, a deep sense of dread. It inspires in some people a deep sense of awe. It inspires in some people a deep sense of insignificance. But I would like to argue that the fact that we took this picture and that we sent this spacecraft on this voyage that it's on is actually an indicator that even though we feel that deep tangle of emotions, that we fear we are insignificant in all the vastness of the cosmos, the fact that we said that we sent the spacecraft says something much more. Okay? And to convince you of that, I'm going to tell you about one other thing about Voyager, which some of you may know, which is it carries on the side something that's not a scientific instrument at all. It carries on the side a golden phonograph record. Okay? The Voyager record is a recording of what we as humans think us and our planet was all about at the moment that we launched Voyager. On the off chance that somewhere, billions of years in the future, when Voyager has left the sun far behind, when our planet almost certainly will be different than it is today, when our species may not even be here, we recorded a message in a bottle. So that if someone happened in all that vastness to find Voyager, they would know something about the people who built this robot. And of course, there's been awesome science fiction written about this. Okay? But let's not think about the science fiction for a minute. Let's just think about the record. Okay? So what's on the record? First of all, there's instructions for how to play the record. Okay? And famously, if any of you are like total nerds and like programming in Python and stuff, right? No one had ever attempted to decode the Voyager record until just a few years ago. And some amateurs, they heard the story I just told you, and they said, okay, don't tell me anything else. they went and got this image, they went and got the audio data from the record, and they wrote a whole bunch of Python scripts to decode based on this instructions to see what they could do. And you know what? They did it. And it was awesome. And so now I have something to do next summer. Okay? So, what does it have on it? It has, with the record, it has a phonograph needle, first of all. So you can play it. Okay? That's hard to find these days, although vinyl's coming back apparently. So, okay. But here's how you play the record with the enclosed photograph needle and what the data looks like. Okay? This is kind of what the data will look like as it comes off and how to do the scan, and then how to take the data and assemble it to make an image. And this is the first image on the record. In the same numerical system that this is described in, this is a map showing the distance to Earth, or the location of Earth in the galaxy. And this is showing you how to count in the number system here using the molecular hydrogen transition, which we assume someone technologically capable will know about, because hydrogen is the most common thing in the universe. Okay? Now, what's on the record? Well, on the record are greetings, spoken greetings in 55 languages of Earth. There is 115 images of life on Earth. There's pictures of ski hills, pictures of mothers and babies, pictures of dissected human organs. There's pictures of cities. There's pictures of forests. There's pictures of desert islands. Okay? It's the 1970s, so, right? These are 640 by 480 pictures. There's 115 of them. Okay? That's all. So this is a fun exercise. Go home and try and figure out what 115 pictures you would choose to tell some distant future about life on Earth today. What are you going to send them? Pictures of JWST? Pokemon cards? Right? What are you going to send them? Right? Do you have a question?
Why dissected organs?
Well, right, so this is an interesting question, right? There were lots of debates about what should we have pictures of. And one of the discussions was we want them to know that life forms on Earth have different shapes and that they have internal complex workings. Because we couldn't send them a whole biology book about how you have to eat food and break it down into simple sugars and then go through anaerobic glycolysis in order to generate energy so you can get up and come to an astronomy talk. But you want to give them enough information that they can realize, wow, the beings are more complicated than just this outer picture shows. Right? These are the kinds of conversations you're going to have for the next 2 months trying to decide what 115 pictures you would have said. Okay? Okay. There is, in addition, 90 minutes of music. Earth's greatest hits. There's a Peruvian wedding song. There is Bach's concerto. In fact, Bach's the only artist on there twice. There's Johnny Be Good, right? Yeah. So there's a famous Saturday Night Live skit. Has anyone seen it? With Steve Martin, where he's playing an alien who discovered Voyager, and he only had one message for Earth, and it's like, send more Chuck Berry. It was great. You should go watch it. Okay, 90 minutes of music, right? So from all the music, it's cross-cultural, right? It's music that's classical, it's rock and roll, it's music that we use in ritual, it's music that we use for entertainment, but only 90 minutes. How do you pick 90 minutes of music? Okay? In addition, there is a final hand-engraved note on the inner track of the record, which you can't see in this image projected, but it was added afterwards. It almost caused NASA to take it off the spacecraft because it wasn't in the specs. They put it on as a whim, okay? But it says, to the makers of music, all worlds, all times. Okay? So, if you want to see all of this, you can go to goldenrecord.org or to NASA's archive right here. It has recently been reissued as part of a Kickstarter by Ozma Records. You can order it on vinyl, and they'll send it to you, and you can listen to the Voyager record at home. Okay?
So on these 115 images, I don't remember anymore, it's been so long ago, but is there anything like on war, or are they always portraying good images of the
Right, so the question is, were there any images showing our conflicts and our wars and stuff? And this was a long, long debate that was had, which was, what do we try and convey about our species, okay? And ultimately, they had a discussion where they decided that our conflicts are part of our culture, and our pictures are really trying to describe life on Earth. That's the gist of how the argument went. And so they they weren't trying to paint a rosy picture, right? But they were opting to say, of the things we want them to know, this is not as important as other things. So, okay? And you could argue with that decision, right? So, and part, you know, there's probably different sides to that argument, because you could argue that, you know, the ability to destroy ourselves is a phase, right? We could just be teenagers and we're going to grow out of that. But you could also be pessimistic and say, well, we've been fighting since the Roman times. There's no way that's true, okay? But, you know, these are the debates that you have, okay? There have been several excellent books written about the Golden Record, and there's some discussion of these conversations in there, okay? Okay? Now, my point to you is this. Sending a message like this, and for the content that you and I have discussed, is not the sign of a species that thinks it's small and insignificant. This is done in the face of how enormous the cosmos is, on the off chance that maybe someone will find it and be curious enough to ask, what was with these strange beings who sent this spacecraft out into the universe? That doesn't feel like someone who feels small, at least to me. Okay? It maybe feels like someone who buys Powerball tickets, but you know. We also do that, don't we? So, okay? So, let's go back to this and we'll call it a night. Okay? So, 100,000 billion stars in the cosmos. So, if you go to your window after a rainstorm and you look at drops of water on the window, in just 10 drops of water, there are as many molecules of water as there are stars in the entire cosmos. Okay? This is why the number of stars is not the biggest number we can imagine. But what some of you may remember is that each of us is made of something like 50 to 70% water, which means in your body there are 100,000 times more molecules of water than there are stars in the entire cosmos. And every one of those molecules of water is made of 2 hydrogens, which is what the stars are made of, and an oxygen, which is what the stars are making when they burn hydrogen and ultimately die. This is what we mean when we say you are made of star stuff. There's more star stuff in you, by counting, than there are stars in the entire cosmos. You are the cosmos made manifest, as we said at the beginning. Why are you here? We don't know. But our philosophical nature says this is what the universe does when it tries to figure out what it's all about. It puts all the star stuff together, it stuffs them in little rooms, and it has conversations about the size and scale of the universe and where it came from and how do we know that. And that is empowering for some, and it is terrifying to others, and most of us kind of drift back and forth between those at random moments, right? Which is okay, right? Be humble. You're made of the earth. We are small, okay? And it's important to remember that there's lots about the universe we don't know. But you have to be noble because you're made of the stars. And of all the species that we know here on Earth, and of anywhere else in the universe right now, because it's the only place we know of any life, we're the only pieces of the universe that we know of that are capable of asking questions about where we came from and why we're here and how big is this ginormous cosmos around us. So feel a little powerful each day and get up in the morning and be like, wow, we can do cool things. And it's not just NASA, it's every one of us. And as amateur astronomers, you hold a special place in that story and in that role that we play in helping all of our fellow citizens understand our place in the universe. Okay? Okay. As always, there's stuff to read. This is a great movie, which many of us are old enough to remember when it first came out. This is Powers of 10. It was made by this husband and wife team at IBM, Charles and Ray Ames. It starts here in Grant Park in Chicago in a picnic. It zooms out to the biggest scales of the universe and then zooms into the tiniest scales of the universe, which you and I haven't even talked about. It's awesome. Okay, it's still great today. Thinking About Life. This is one of my favorite books. This is a coffee table book by Rachel Sussman called The Oldest Things in the Universe. She went, Oldest Things in the World. Sorry, the world, the universe, same thing. She went around the world and visited the bristlecone pines and the elephant grass in the Balearic Islands and just all the oldest stuff that she could find and took pictures of it and kind of reflects on the scale of life on Earth. Okay. Carl Sagan, Cosmos, this is very relevant for many of us who grew up at the right time. Carl Sagan's the one who first made us start thinking about these things. This, for those of you who are music fans, this is Peter Mulvey. He's a folk artist in Wisconsin that I like a lot. This is a great story he has. He has this album called Letters from a Flying Machine. And this is about him sitting out behind a hotel in West Virginia with his physicist buddy Vlad, asking why we don't know about aliens. And it's far and away the most clear and lucid description of why we're not sure if we're the only beings in the universe or not that I've ever heard. Okay, so it's a great one. Okay, this is a link to a TEDx version, 10-minute version of this talk that I gave. So if you want to hear this in 10 minutes quick without all the stuff, you can go watch it there. Okay? So I'll leave you with the Carl Sagan quote and call it a night and say thank you for your attention. And I'm happy to take questions for as long as people want to chat. So.
Suddenly occurred to me about the Golden Record. Did they say anything about God or a concept of God?
Yeah, so the other than the music, I don't think there is any, like in any of the pictures or any of that, there is not. Yeah.
Who's in the room when they decide what to put on a record?
So there was a team of people. It was led by Andrian, Carl Sagan, Tim Ferriss, can't remember who all there. And they made initial recommendations and suggestions, but then what they did is they polled scholars from around the world. So when they were selecting music, they asked music scholars. When they were selecting pictures, they asked biologists, and geologists. So they tried to incorporate as much of the kind of broader group of people as they could. There was a lot of sensitivity around this. Some of you may remember there was a plaque on Pioneer, and that caused a huge uproar because the plaque was just an engraving, but there were two human figures on the image, and they were nude. And so this caused an enormous argument about whether or not we should be sending pornography to aliens. Which, so they tried to be more careful when they did Voyager. So. Yeah.
So you talked about the scale of the universe. Is there a way to know if it's infinite or not?
Okay. So we haven't, I don't think we've done the cosmology talk. We'll do that sometime, but that's a great question, okay? And every time someone asks me this question, I apologize because I'm going to ask you a question first, okay? Which is, what do you mean when you say the word universe? If we're going to ask, is the universe infinite, then we have to know what we mean when we say the universe. So let's just, you and I, talk about what we think an operational definition should be.
Is space in which physics are the same.
Okay, that's a good one, actually. I like that. Okay, so that's kind of discussing a volume, right? And indeed, the Copernican hypothesis says that everywhere that you and I can see, physics or the laws of physics are the same. But I want to take a slightly broader definition. So let me suggest to you the following definition. The universe is everything that exists.
Unless you believe in multiverses.
Okay, well, right. But this is the important point, right? And the reason this is an important point is because when we talk about universe, we are often very sloppy with our language. And what most of us mean when we say universe is not the universe, which is everything that exists. It is the observable universe, which is what can I see with a telescope? Okay? And the observable universe is finite. Okay.
Some folk think at the edge, if it's accelerating faster than the speed of light, space is expanding, then you won't be able to see it, right?
The observable universe is finite. The universe is finite in age. The speed of light is finite in size, so there's a finite distance it could have traveled.
That we can measure.
Measurement is what you can measure, and you can't measure anything that wasn't there in the amount of time light could have traveled to you, right? Now, beyond the edge, there could be more, but that's not the observable universe, that's the rest of the universe, okay? So you have to be careful, right? And the universe, the observable universe, can be doing weird things. It can be stretching, it can be changing shape, it can be accelerating, but that doesn't change the fact that it's observable. And it doesn't change the fact that you sitting over there can observe a different universe than I observe standing over here. Because you and I are standing about 20 light nanoseconds apart, and so you can see 20 nanoseconds more of the universe in that direction than I can, and I can see 20 nanoseconds more of the universe in that direction than you can, which means you and I are not looking at the same observable universe. And that's supposed to melt your brain, and it's okay if it does. Okay.
So, a couple questions.
So it doesn't just work for rainbows, huh?
Yeah, it doesn't just work for rainbows.
When I hear about the Big Bang, I always hear that everything started as a point mass, or point. And I can't wrap my head around everything in the universe, being at that point.
Yeah. So the statement is usually something like, everything in, I'll insert the word, the observable universe expanded from a space smaller than the period at the end of this sentence. Right? Okay? And what that means is not everything came from that point. It means everything that you can see from there expanded from that point. And everything I can see from here expanded from this point. And everything he can see from there expanded from that point, and everything she can see from there expanded from that point. And just like gigantic soap bubbles, they all expanded together. Okay? Now, it's incomprehensible to us that all of the stuff in this room used to be squeezed into a point, and the sun and Jupiter and the galaxy and all the 500 billion galaxies, blah, 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 blah. Okay? But that's okay. Because the other thing that usually doesn't get said, but does hold true, is that the laws of physics as you and I understand them break down and do not describe that point from which everything expanded. We don't know what it was like because we don't have any way of describing it in terms of what we can measure, experiment on, mathematically describe, or understand. Okay? And that's what the whole future expansion of quantum gravity and string theory and all of that is messing around with, is trying to get to the point where the laws of physics can tell us something about that point.
So the other question I have is, we talk about dark matter, and the dark matter is supposed to be an answer to the fact that there's more gravity than there is light that would.
That's one of the measurements. That's right. Yep.
But with James Webb, are we starting to see more stuff? And at some point, we're going to go, oh, never mind. Looks like we didn't find it all.
Well, yeah, so that picture that I showed you from the first light images, one of the things we can do with that picture is measure how much light and how much gravity is in the center of that picture, because we can measure the distortion of those galaxies, right? And so this will be something that we do. I don't anticipate the answer is going to be different, but we're not I was going to say we're not so dumb that we're not going to make the measurement again to make sure. So, but we don't know what the dark matter is, which means the answer could still be anything. So, like we've measured things wrong. That's still possible. Most physicists don't think that, but we'll see. Okay, here and then here. So,
when we're looking at the cosmic microwave background, are we looking at the edge of our observable universe, or what does that entail? Because I mean, we see those Planck pictures, but they say it goes back about 380,000 years after the Big Bang. But are we looking out to a certain distance, or where is that cosmic microwave background?
Yeah, so that is a certain distance. That is not the edge of the observable universe. That is the distance of the edge of the observable universe in light. Okay? We can get from beyond the cosmic microwave background, although we still have not done it, we can get neutrinos and other subatomic particles that are not readily interacting with matter, and we can also get gravitational waves.
So when we see that CMB, is that further than the galaxies that we saw in that picture?
Yes. So in fact, one of the things that we do in modern research is we take the scale of all of those spots on the CMB, okay, and what those are telling us is how much matter is in different places when the CMB was generated. And we use that to understand how all the matter in the universe clumps together and ultimately grows into galaxies. Okay, and so we're getting better at understanding that, but I would say that is still an area of current research. Okay, because we can't make big enough computer simulations to guarantee that we've got everything quite right yet. Okay, but we do it, right? And we have these those of you who are interested in this, go look up, what's the name of the simulations? We grow galaxies with dark matter, gas, dust, stars, illustrious. Go, and you can find movies of the illustrious universe growing. And it's just a cube of the universe filled with nothing except dark matter and particles when the universe began. And then we grow galaxies, and we say, does it look like the universe today after we do it? So, okay, it's very cool. Okay, and that's just one of many, but illustrious is kind of one of the most famous ones. So, okay, yes, right here.
So it seems like whenever I hear these kind of talks, that our lack of knowledge actually hinges on the fact that our maths are not capable of explaining the parts of our lack of knowledge. And what's the next step? I mean, we would have to invent a whole new math, just like,
Yeah. So are you thinking specifically about the early universe and the Big Bang singularity? Yeah.
Because we can't describe infinities, and we can't describe division by zero even. I mean,
So I mean, the laws of physics as we understand them always are at the boundaries of what we're capable of measuring, because we can describe all kinds of things mathematically, which the universe is not obliged to do. Right? So there's a whole area of cosmology called relativistic cosmology where I can write down descriptions of universes that are not our universe. Okay, those of you who read about this, we are in what's called a Friedmann-Robertson-Walker universe. That is one solution, cosmology solution of general relativity. There are plenty of others. Okay, like there's this whole classification scheme called the Bianchi scheme, right? But the point that I just said is the important one, which is our ability and our need to describe things mathematically is always at the limit of what our experimental capability is. So when Einstein sat down to write down general relativity, there was a long-standing problem in Newtonian gravity, which was the orbit of Mercury didn't look right. Mercury was its precession, is slightly elliptical, and that ellipse is moving at a rate that was measurable by experiment, but which could not be explained via the law of gravity as we understood it. But general relativity nails that number, spot on. Okay? And so now we're at this point where we have theoretical descriptions of the early universe and the singularity, okay? But we don't have any experimental data to do it, right? Because it's all hiding behind the cosmic microwave background. So the day that we can detect gravitational waves from the early universe, that will be the very first probe that we have of these moments, back at this moment in time, the Planck era as we call it, where the laws of physics as we understand them don't work. And that information will be invaluable about guiding us towards the right understanding that may or may not be the way the universe works.
So just like the telescope was opening
Yes,
up that
that's
whole new
right.
thing, we need a
Yeah.
new tool that is going to open up.
That's right.
that would-
And it's
something
this
like
kind
this,
of,
stuff like that.
stumbling walk that we make between observations and tools and experiments, mathematical capability and understanding, right?
Yeah.